For my final project, I decided to perform statistical analysis on factors that influence life expectancy. This data set was originally collected by World Health Organization, but I found it on Kaggle, so that final data set on Kaggle has information for years 2000 to 2015, and it has statistics for 193 different countries. So here's the factors that were introduced in the data: country, year, status, that's if country developed or developing. That's the only categorical data that I have. There are mortality rates for different categories, alcohol consumption, measles cases. There's some immunization information, total expenditure. This is the amount of money that is spent on healthcare. Percentage expenditure. This is percentage of GDP that goes into health spendings. GDP is a gross domestic product. Population, body mass index, gross domestic product per person, income composition index. That's a number from 0 to 1, with 0 being no opportunity to earn income. Schooling years, thinness among 5 and 9 years olds, thinness among 10 and 9 years olds, and HIV cases. Our target variable is life expectancy. I found that the minimum was 36.3 for Haiti. I thought it was very, very low, and I started looking into it. So that could be because of the year, the 2010, and for that year there was earthquake that killed a lot of people. So that kind of made sense. I just wanted to make sure that there's no kind of unrealistic values, and 36.3 seemed very low. Maximum is 89 for Belgium, Finland, France, Germany, Italy, New Zealand, Norway, Portugal, Spain, and Sweden. So when I plotted the original life expectancy data, we see that the distribution is left skewed. I also tried to see what the trend looks like year by year, and we see that the life expectancy increases year by year. I just wanted to double check that just to make sure that what I have in the data makes sense. So I decided to find some data for these years and just compare to what I see in my data. So I found this visual. I thought it was pretty good to kind of get an overview. So we see that the darker the colors, the higher the life expectancy, and we can compare year 2000 and 2015 and see that obviously from most of the countries, the life expectancy increased for this 15 years. So it makes total sense. It's also not surprising, but to see that Africa has the lowest life expectancy today and back then. Looks like America has one of the highest numbers. We'll also see that Australia has pretty high numbers. So I just thought it was kind of good to compare. We first trying to just create new model, which is we ended up with mean at 69.2 and standard deviation 9.5. So our 95% error bounds would be 50 to 88. So this would be the kind of, if we look at standard deviation as a sigma for our linear regression, we're trying to beat that value. So we're trying to come up with a model which sigma is below 9.5. So we kind of make some presumptions before modeling, trying to see which would be positive factors and negative factors that influence in life expectancy. So obviously year developed countries would have higher life expectancy, and just most of these are kind of obvious, but some of the, for example, thinness, at first I thought it was basically for if children BMI is within like healthy range. So that's what originally I thought it was, but come to find out, this is rather for like sick thinness. So basically, the statistics of how many children out of for each thousand of population are like ill thin. So it's definitely negative factors. I also I put question mark next to BMI because BMI not necessarily a negative factor, but if it's too high or too low for the country, then this could be considered a negative factor. I also found a lot of missing values in the data. I end up using the K nearest neighbors imputing to fill in these values. I think like all in all, if I was to exclude that data with missing values, I would lose like half of the data. I also believe 10 rows for target variable were missing, so I had to remove those. So, but overall, most data looked pretty reasonable to me. So, for our linear model, we always want to start with a full model. So this is what I did. I plugged in just every column, every variable that I had, every factor, and right away we came up with a model that has sigma of 4, which is compared to 9.5. This is more than twice smaller error, sigma, and the R square is 0.83, which is not bad at all. Adjusted square is also near 0.883. I've also looked at the residuals. I've looked at all, but just posted a few here. We can see that there's some heteroscedasticity going on. There is, for adult mortality, for example, we can see there are 2 groups of data. So I figured that would be something that to resolve. So while performing the EDA analysis, I was also trying to come up with ideas of how I can improve this model. So after running this model, I was trying to compare the predictions and what model showed, and I found some that are the mixed probabilities, but I found 3 of them that are weak and made no sense. For example, my model showed that the year coefficient is negative, so basically as with time, life expectancy should decrease, and I just showed in earlier slides that this is not the case at all, so that didn't make any sense. For hepatitis B vaccination coefficient is negative, which made no sense. It's mean basically the higher vaccination rate, then the lower life expectancy. Didn't make sense. Also, infant deaths coefficient was positive, which would mean that the more infants die, then the higher is life expectancy. So this 3 didn't make sense, and I realized that I will have to remove them from before running my final model. As I said previously, from performing EDA analysis, I concluded that I need to do some transformation. The biggest issue was the big range of data. So for example, with population, we had some countries with literally like 100 people population and some that had a billion population. So I had to perform the cube root transformation, square root transformation. It depended. I just did it as I did EDA analysis because some of this data pretty much had to be scaled because of how huge these ranges are. But I also performed some third power transformation just to improve my residuals, and you can see that I also got rid of this grouping trend that was going on, group trend was going on here, but overall that after I removed 3 variables that didn't make sense, and not the variables, but the coefficients, and after I performed rule transformation, I end up with actually a better model. My R squared went up to 0.86, and as well as adjusted R squared. And my sigma went down from almost 4 to 3.55, which is much better. So this is, I try including some interaction terms, but they didn't seem to make any difference whatsoever. So I just decided to proceed with this final model, and I performed cross-validation. And here's the confidence interval for sigma and R squared, which that looks good to me. Nothing raises red flags. So this is my final model. Then I did learning curves to see if, more data would improve our model, and we can see that our curves converged. So more data most likely will not improve our model, but we also see that it converged to around 3.5 value, which is much better than our target sigma that we're looking for, which is we're trying to just get anything better than 9.5. So we conclude that this model has a good performance, and sigma is not too high, so we can't say that it's high bias. So finally, we came up with this model, so we're going to try to put that to practice and make some predictions. I came up with 3 different cases. I'm not going to go through what the values are. You can just kind of see what I tried here. So for the first case, we ended up with a prediction of 51 years, and error bounds are 44 to 58. And if we compare that to null model, we see that if we use the null model, we would have the prediction is pretty far off from what we ended up with linear regression model, and we see that our error bounds are much tighter for our model than for null model. This is almost 38. The range is 38. For case 2, we ended up with 58 years, and error bounds are 51 to 65. Again, this is the value is pretty far from the 69, and especially for case 3, the prediction is 47, and we see that this is very far off from it. If we use the null model, we would have a pretty poor prediction. So overall, that I believe my model end up being reasonable, and it looks like we can go forward and do predictions with it. Thank you so much.